2.2 on polynomial functions. So we're going to look at some more parts of the polynomial function to determine where the zeros might be, how many zeros there are in a function, and in behavior. So each section in this chapter we're going to be finding more and more things or characteristics of polynomial functions. So example 1 wants us to graph this function to describe the end behavior of the graph using limits, and then explain your reasoning using the leading term test. So this function f of x equals x minus 3 to the 5th power. So I have a chart that we're going to look at first before we come back to the problem. So we talked about this in chapter 1, that we're always looking at the highest exponent of a polynomial and the coefficient of that term. That determines what the end behavior of the graph is. So in chapter 1, we used rises and falls left or right. In this chapter, they want us to be more specific and use limits to describe the end behavior. So I've written the terminology in gray, but then the limit is in black. They mean the same thing. We're just trying to transition into the limit terminology instead of words. Okay? So back to this problem now. The highest exponent, I could multiply out x minus 3 to the 5th power and multiply that all out. But I don't have to, because in the end what would happen is it would wind up being x to the 5th power plus a whole bunch of other stuff. Okay, so the 5 tells me that's the highest exponent, and then the leading coefficient, well, it would wind up being x times itself 5 times, so that's just going to be 1x, and that's positive. So since the highest exponent is odd and the leading coefficient is positive, that tells me that it falls left and rises right. But we're going to use the limit terminology, and we're going to say, and you can flip-flop this either way, it doesn't matter which one you write first, but as x approaches positive infinity, so as we're going to the right, f of x approaches positive infinity, then the function is going up. Then the second half says as x approaches negative infinity, which is as we're going to the left, f of x approaches negative infinity. It's going down. Okay, so that is the end behavior in terms of limits. Now, you can type x minus 3 to the 5th power in your calculator and graph it. So here's what the graph looks like. It looks very similar to a cubic function, and you can see it's going up on the right-hand side and down on the left-hand side, and it crosses at 3, 0. Okay, example 2 says to state the number of possible real zeros and turning points for this function, x to the 3rd power plus 5x squared plus 4x. Then it says determine all of the real zeros by factoring. Okay, so here's the rule that we're going to use on this example. It says that a polynomial function of degree n has n distinct real zeros and n minus 1 turning points. So the n that they're talking about is the highest exponent of the polynomial function. That tells you what the degree is. So this is a 3rd degree polynomial. That also tells me how many real zeros there can be for this function, and how many turning points there are by subtracting 1 from that number. So I know that there are going to be 3 real zeros, 2 turning points. Now we're going to take this polynomial and factor it to find all of the zeros. So first thing I notice with this function is that they all have an x in common. So I'm going to factor an x out of each term, and I'm going to leave that x out front. So I'll be left with x squared plus 5x plus 4. So I've noticed I have a trinomial that I can factor again. So I'm going to split that up into 2 parentheses. So I know x times x equals x squared. I need 2 numbers that multiply to get 4, but add or subtract to get 5. So that's going to be 1 and 4, or 4 and 1. In this case, since they're both positive, it doesn't matter the order that they go in. Okay, once you have completely factored a polynomial, you set each of those factors equal to 0 and solve. So then x equals 0 is one solution, x equals -4, and x equals -1. So these are the zeros for this function. You could graph this polynomial and you would see that it does cross and touch those points on the x-axis, and it does have two turning points. So 2 times that the graph turns and switches directions. Okay, number 3 says we have this function x times 3x plus 1 times x minus 2 all squared. We're going to use the leading term test to determine the zeros, and we're going to find the multiplicity of any repeated zeros. So the word multiplicity is new. This means the number of times that a factor appears in a polynomial is the multiplicity. If the multiplicity is even, the graph touches at that 0. If the multiplicity is odd, the graph crosses at that 0. So how many times a term is listed or a factor is listed when it's all factored out determines what's actually happening at that point, if it's crossing or touching the x-axis. So we're going to look at each of the factors and talk about the multiplicity and what it's doing there. So the first factor is x equals 0, and since it's only listed one time in this factorization, it has a multiplicity of 1, and that means that the graph crosses the axis at 0. So because it's only there an odd number of times, then it actually crosses the graph. The next factor is 3x plus 1. If I solve that, x is going to equal -1/3. That factor is only listed one time. So it has a multiplicity of 1, and it crosses at that point as well. The next factor, x minus 2 squared, if I solve this, x will equal 2. Now this time, I could rewrite these factors as x minus 2 times x minus 2. Or because the 2 is there, that tells me it has a multiplicity of 2. Now since the multiplicity of this factor is an even number, then that means that it just touches the graph at this point. It doesn't cross. Okay, so let's look at the graph for this function, and we'll talk about each of those points again. Okay, so here's the graph of this function. If I multiplied everything out, I would wind up having x times 3x times x squared would be 3x to the 4th. That would be my very first coefficient. So since it's to the 4th power, we know that in behavior is doing the same thing, and because it's a positive 3, then they both be going up. So these rise on the left and right. Okay, then you can see these 3 points where it touches or crosses. Starting on the left-hand side, that first point is -1/3, so it crosses there because it had a multiplicity of 1. Then it crosses again at 0, multiplicity of 1. And then it touches at 2, which is where it had a multiplicity of 2. And since this would have been 3x to the 4th power, it does have 3 solutions. 4 would be the maximum number of real solutions, but it does have 3. And then you can see that it does have 3 turning points. Okay, so 3 spots in the graph that actually turns direction.